Hi, good morning and good afternoon, everyone. Thanks for joining us today for this new Severalnines webinar. My name is Jean-Jérôme and I'm with the Severalnines team. I'll be looking after you today for the next hour or so. Before we get started, I just wanted to give you a few details on our logistics for this session. First of all, you can ask questions at any moment, of course, by using the question section of your control panel and or the chat box. Also, you've got these two options. The question section is usually a good place to go to ask questions. Either on the system or on the content that you're going to be hearing about today. And you can also contact us after the webinar at this email address here that you can see on your screen, info@severalnines.com. And we'll be happy, of course, to continue the conversations there. We're broadcasting from Dublin today. We're at the Percona Live conference. It's good to be here, and we're taking some time out to talk to all of you now about Docker, and we're going to get started with that shortly. Exactly, but I just wanted to give you a quick introduction to Severalnines and ClusterControl before we get started with the Docker topic. We are a company that specializes in automation and management of open source databases. We focus on these four main areas, which are deployment, monitoring, management, and scaling. And we have a product that does that called ClusterControl, which comes in a community version where you can deploy and monitor for free for as long as you want. And we also have a commercial version that includes management and scaling features, which you can test for the first 30 days of your download when you download ClusterControl for community. It covers these areas, as I said, and you can see here in more detail what that means, around deployment, around monitoring, some of the key features here. And some of the key features are on management, with automated recovery, backups, database upgrades, and so on. Feel free to check it out, of course. We encourage you to check out ClusterControl or ask questions about it. And we've got quite a few, these are the databases that we support, all of the different MySQL flavors. We've got MongoDB by Percona and by MongoDB. And we also support Postgres, of course. And finally, we have over 32,000 deployments of ClusterControl. You can see some of the users that we currently have and some of our customers, which are listed here in this widespread of logos and names. But for now and for today, the topic is all around Docker and MySQL on Docker. Thanks for joining us. It's all around understanding the basics of Docker. And before we get started with my colleague Ashraf, to whom I'm going to hand over shortly, I just want to ask all of you a quick question. And this is it's kind of basic, but just to ask whether you're currently a Docker user yourself. And it'd be great to get your feedback here. I'll let this run for a few seconds, and I'll share the results then of the poll once everyone had a chance to participate. Thanks for providing your feedback. I'm just going to close this now and share the results. Okay, so this is nice. It's a nice split, actually. So nice to see some of you testing. 1/3 of you are testing Docker, which is good to see. Or you're planning to look at Docker and get started with it. But 17% in production. That is really interesting to know. We'd love to hear more about how your experience is with Docker in production. And then some of you are curious, and so it's good to have you with us. And the talk today is based on Ashraf Sharif's blog, MySQL on Docker, Understanding the Basics, which you might have read already, but this is the live version. And so I'm pleased to introduce Ashraf, my colleague, the author of this blog, and I'll hand over to you now, Ashraf, for the presentation.
Thank you, JJ. Good morning and good afternoon. My name is Ashraf Sharif, and I'm from Severalnines. In this webinar, I'm going to talk about understanding the basic on how to run MySQL on Docker. Here is the agenda. We are going to look into a brief introduction to Docker. Then we are going to cover from one Docker component to another, followed by ClusterControl on Docker and Q&A session. Docker allows a rapid deployment of containers by using a pre-built image. Every container has its own file system and process space, which are not visible to other containers. and also a network stack, where each container will be assigned with at least one network interface. So due to this isolation, containers won't affect the machine host process or file system, which then allows you to get a greater density on the physical host, reduce conflicts between various deployment environments like development, testing, staging, and production, and also increase the deployment speed. So Docker consists of several components out of the box. Docker client is what you use to interact with Docker engine daemon by running commands prefixed with Docker and followed by an action. Docker daemon is the engine you install to manage containers, images, networks, volumes, nodes, and also accessible through Docker REST API. Another component is registry, which is the repository to host your Docker images. So we are going to look into our the first component of Docker, which is Docker image. Docker image is the first thing that we have to look when familiarizing with Docker, because in order to run a Docker container, you have to have an image to start with. Imagine image is actually like a template. It has all the required stuff to run the containers, and that includes the software and the code, binaries, dependencies, libraries, environment variables, and configuration files. There are two ways to create an image. The first one is by committing all the changes of a container, and the other one by using a more declarative approach defined inside the text file called Dockerfile, and then we use it together with Docker build command. Once the image is built, you can distribute it to other hosts manually using tarball, or push the image to Docker's image repository. We called it registry. Yep. And Docker Hub is the most popular public registry. It stores thousands of Docker images and supports automated build, where it can hook to the code repository like GitHub and trigger build when it sees a new commit being pushed. You can use image published and maintained by the application vendor itself, or use other user contributed image, or you can create your own image to suit your needs. Public registry like Docker Hub is very helpful for public and open source images. However, for your company's private images, you should go for a private registry, either by subscribing to hosted services like K.io, Amazon EC2 Container Registry, or Google Cloud Registry, and so forth. So you can also opt for self-hosted private registry if you have enough resources for processing, bandwidth, and storage. So the last comment down here can be used to simply start your own Docker registry service running on port 5000 on the Docker host. So building an image by committing the changes is similar to the standard MySQL deployment procedure on host. So on the left side is the simplest step required to install run a MySQL server on Ubuntu. So on the right side is the Docker equivalent steps. With this approach, one would start by pulling a base image and start a container based on this image. Then we make the required changes directly into the container, like installing MySQL packages and configuring the MySQL configuration file. Once we are good, we can then just commit the container into a single image with a username, which is my image, and then followed by / and then followed by an image name, which is MySQL, and also an optional tag. In this case, we are using 5.7. You can the default value is latest if you missed it. So, excuse me. When the container is being committed, the running processes will be paused to reduce the risk of data corruption. To run the container based on this image, and then one will use Docker run command with the image name, and then followed by the execution command, which is MySQLd, and followed by the configuration variables for MySQL. Using Dockerfile to create an image is much simpler and declarative. Dockerfile is a text file that contains all the instructions to build an image. The build process is executed by the Docker daemon, not the Docker client. And Dockerfile is the preferred way to maintain your Docker images. It can be integrated with Docker registry to provide continuous integration and much more clear to see what is provided by the image. As you can see here, we know that the image runs on Ubuntu, have a MySQL server installed with a custom my.cnf. And also by default will expose port 3306 when container is started. So when building your image with Docker, each action taken, for example, apt-get install MySQL-server will form a new layer on top of the previous one. An image is simply a collection of layers stacked on top of each other, and this layer will be read-only once it is built. These base images then can be used to create new containers. You can see the layers by using Docker history command. So the layers in red are related to our Dockerfile commands, while the green layer are inherited from the Ubuntu base image that we have defined in the Dockerfile. So as you can see, the biggest layer is occupied by the apt-get install MySQL server with which is 370 megabytes in size. So there are tons of MySQL container image available on Docker Hub that we can reuse and enhance with more functionality. So inheriting this MySQL image allows us to leverage the work done by the maintainer. So in this example is the Docker team. So also to increase the deployment speed, try to keep away unnecessary stuff inside the image. Just install whatever requires by MySQL server and clients, and that should be sufficient. There is also a popular tiny image called Alpine, which comes with its own package manager. And MySQL MariaDB packages are there too. And you can use Alpine as base image and build your own MySQL server around it. The base image is just 5 megabytes in size roughly, while the Ubuntu base image is around 190 megabytes in size. So when you want to build your custom MySQL image and you want to run entry point script during container startup, make sure that the last command of the script starts with exec and then followed by the main process of the container. In this case is MySQL D, and then this process will hold PID1, process ID1. So during the container runtime, and this is very critical when stopping the container later on. So only process with PID1 receives the proper signal when stopping the container. Also try to follow the general guidelines when writing Dockerfile, especially when you are building a public image, so anyone else can easily understand the content of the image and contribute to it. So the next component is Docker container. To run a database container, we have to understand how Docker stores data inside a container. Let's take a look at this example. On the right side is the command that I use to run a MySQL container. Docker run is basically a combination of 3 Docker commands: Docker pull to pull image, Docker create to create a container, and Docker start to launch the container. So in this example, I'm using the standard MySQL image published and maintained by Docker, which is available at Docker Hub. So this MySQL image is a general purpose image, which you can define a number of environment variables to suit your needs. So this image requires MySQL root password environment variable to be set during startup. With this one, we did not define any volume. So if container is running without a volume, all the directory or file modifications in the container will be written in the container layer, which is the upper layer on top of the image layers. The image layers are read-only, while the containers layer up here are writable. So this part is also known as stateful layer. These 2 layers run on union file system, depending on the Docker host operating system. For Ubuntu, it's default to AUFS. For Red Hat and CentOS, it's default to overlay FS. So in this example, I'm using an Ubuntu host which running on AUFS. As you can see, the container layer only utilizes around 4 bytes of disk space once started, and you can verify this using docker ps-s command. So when creating another MySQL container using the same image, you are actually creating a new writable layer to store data for the container. Each container has its own writable container layer, which means multiple containers can access to the same underlying image and yet have their own data state. So when you remove a container, you are basically removing the writable layer out here. So all the changes inside the container will be removed as well. So this layering and unification technique is very space efficient, minimizes I/O operation on the host, and also support caching. So you can imagine the layers as directories. When you modify an existing file, like for example, /etc/mysql/my.cnf, so the container layer will first, the container will first look up this file in the container layer. So if the file does not exist, it will go through the image layers starting from the top and look down for this file. It then copies the file from the image layer to the writable container layer. So Docker will then write the changes to the new copy of the file in the container layer, as shown in operation 1. So this is known as copy on write operation. So in example operation number 2, we are trying to create a new schema and table, which means a new directory and file shall be existed in the container layer. So when you create a new file inside the container, Docker will create a directory or branch in AUFS term with a random SSH256 hash name and place that file inside that directory with metadata, including a pointer to the parent directory. So you can see this file directly inside var lib docker AUFS. So Docker supports a number of copy on write file system and devices like overlayFS, device mapper, and ZFS. Each storage drivers handle the implementation differently, but all drivers use stackable image layers with this copy on write strategy. So Docker works great in deploying, managing, and scaling stateless application. Stateless means that the application simply doesn't hold any state and doesn't care about each other's state. It can come up and go, and it doesn't break a thing about your application as a whole. Generally, stateless application is usually lightweight, scalable, and easily reproducible. And it doesn't store any data persistently. And traditionally, people will deploy the persistent data tier outside of the Docker user space, like using database for MySQL or something, or object storage in Amazon S3. Stateful application like data service is totally the opposite of those. It requires more attention when a container's state has changed within the environment. For example, imagine a scenario when a master node goes down in a master-slave replication setup. We must be extremely careful when promoting another slave to ensure no data loss during the failover operation. Typically, stateful application requires data to be persistent and are tightly coupled with other containers if running in scale. So the next component is Docker volume. Since Docker 1.9, it is possible to store data persistently in name volume using the local volume driver. Before that, only bind mounts was supported. The problem using bind mounts was it is very dependent to the host. If you wanted to mount existing data, you would need to make sure that that path exists on the host. One good thing about bind mount is you can mount a file instead of a directory. So using name volumes is much simpler and more independent. Docker creates a directory under var lib docker volumes, and the volume can be referred by other containers using just the volume's name. So the volume contents exists outside of the container lifecycle. So since Docker manage the directory's content of name volume, it can be extended with external volume plugin instead of relying on the local volume driver. So this has opened a new door for stateful application to run efficiently in Docker. So you don't have to worry about containers upgrade, or even if the containers were killed or crashed. So if you run with a persistent storage mounted inside the container, the other containers can just pick it up from the last state. Also, you can have another volume dedicated for storing non-persistent data in RAM, or swap if memory is low, similar to RAM disk. So MySQL can leverage this type of volume for temporary data directory, which is known as TMP. To store data persistently, we will have to configure a couple of extra options related to volume. You can create the volume first, or just directly specify under the volume flag under Docker run command. So Docker will create the volume if it doesn't exist. So this command tells Docker to create a volume inside var lib docker volumes directory on the host file system. If it doesn't exist, and then it will mount it inside the container under MySQL data directory path, which is var lib MySQL. You can also access the data volume directly from the host while the container is running. Volumes are often a better choice than persisting your data in a container's writable layer, because using a volume does not increase the size of containers using it, and the volume's content exists outside the lifecycle of a container. Starting from version 17.06, you can use a mount flag, which is much more verbose. So this command down here also does the same thing. Originally, mount options are meant for Swarm service and not for standalone containers. With mount, the order of the key value pairs is not significant, and the value of the flag is easier to understand. So when a file that you want to read or modify is mounted to a volume, it will bypass the container layer and operates at the native host speeds. So you can mount any number of data volumes into a container. Multiple containers can also share one or more data volumes. However, you cannot share the MySQL data directory, because one and only one process is allowed to access the MySQL directory at a time to prevent conflicts. So what if the physical host itself got a power cut off or crash or blew up? So you will lose your container as well as the persistent volume together with it. So to recover from this scenario, we can use a volume outside of the localhost. So the simplest setup would be using NFS, which allows you to export a directory to another server through network. This directory can be mounted locally on the client host, which is Docker host. You can then use the bind mount approach to mount the directory inside the Docker container. So in this example, we mounted NFS export in the Docker host and the /NFS directory from a remote host 1.100. Also, take note that there are a number of considerations when running MySQL on NFS. So just read that link for more info. In MySQL, the most important path is the data directory, and by default, it is under var lib MySQL. This is the default the data directory path in MySQL, and you can customize this at a later stage. Despite I don't recommend this for the sake of simplicity. When running MySQL on containers, you are expecting them to run in a more uniform and organized way. So try to minimize the complexity of your MySQL configuration options and stick to the default options is possible. So by default, most of the files or directories generated by MySQL are default to data directory. Apart from that, if you would like to use your custom myCNF, you should preserve etc my.cnf.d, which is the MySQL configuration directory, and then store your my.cnf file under this directory. If you're using any other MySQL plugins, you might also want to preserve base directory /lib/plugin. This directory can be mounted as read-only using the mount flag in Docker. This is actually the recommended way to prevent the MySQL plugin to execute any arbitrary code. So MySQL also generates non-persistent data like temporary files under TMP dir variable. By default, MySQL will use /tmp or /var/tmp or /user/tmp. Some select statements, especially when sorting using group by or order by, will create temporary SQL tables. You will see a file prefix with SQL underscore exists under this operation, during this operation. And you can mount this directory inside the container using the tmpfs volume instead, which is only stored in the host machine's memory or swap if memory is low, similar to mounting in a RAM disk. So when the container stops, the tmpfs mount is removed. If a container is committed, the tmpfs mount is not safe. However, there is a caveat. Beware if you are having a huge sorting that occupies more than the limit, because when this happens, the host will start swapping. So to avoid this, you could also use the standard name volume for /tmp. So please use this feature with caution. And also tmpfs only works in Linux containers, not for Windows. By default, the storage driver is local. So that means if you create a name volume, the volume will be created on the physical host where the container resides. If you have multiple Docker hosts and you will expect them to scale out in the near future, you should use the volume drivers plugin to reduce the complexity of provisioning each Docker host as the storage client. For example, if I run this command down here, this will create an EBS mount using a volume driver called Rexray, which I already installed through Docker plugin install command, then mount it into the container automatically. You can then manage the volume using Docker volume command. When you delete the volume driver itself will do the necessary cleanup for you. So volume drivers also allow you to extend Docker's volume capabilities, where some storage systems support encryption at rest, volume snapshot, and also backup. It's up to you to choose your preferred backend storage platform. As you can see here, the orange color boxes at the outer layer are storage platforms or file system. They are supported by various Docker volume plugins, which are represented in green. There are lots more, and you can check them out at Docker's documentation page. Whenever you decide whatever you decide to use, please benchmark and stress it to see how reliable your choice is. So what is the trade-off of having MySQL database mounted through remote storage? The first thing is performance. Don't expect it to be as good as the local disk or direct attached storage in the Docker host, especially if the remote storage is shared among multiple hosts, which make it a busy endpoint. MySQL is a disk-based database, so where it needs to flush stuff into disk for persistency. So this performance matters. Here is the simple benchmark that I've come up when comparing the local disk and other remote storage with a simple create table job. So the tests were repeated for 50 times on each storage driver. You can see the green dots, which is remote NFS storage, is around 40% slower than the local disk. With some further tweaking, using a couple of NFS mount options, we could get around 10% improvement over the default NFS as shown by the orange dots. And the red dots represent EBS volume without provision IOPS, where the results are pretty inconsistent. And this setup should be sufficient if database performance is not critical. For instance, in testing and development environment. And don't forget to always perform benchmark on your preferred storage system. Before we go to the next chapter, I would like to pass the microphone back to JJ for the second poll question.
Great. Yeah, thanks, Ashraf, for this first part of the introduction to MySQL on Docker. And just a quick break to ask all of you who are currently with us this question. And it's whether you're currently running MySQL on Docker yourself in a Docker environment. It'd be great to get your feedback here, whether it's for testing purposes, or you mightn't be running MySQL in a Docker environment at all, or you're planning to, or you're just curious, or maybe you'll be in production. That'd be pretty cool to see. But I don't know if we'll see it today. Let's find out from the results. Thanks for participating in this poll. I'll leave the latest on for a few seconds, and just to remind you that you can, of course, ask us questions at any moment by using the question section of your control panel. We'll take a few minutes at the end of the presentation to answer your questions if there are any. But for now, thanks for your participation here. I'm just going to close this now and share the results. Okay. So interesting, because I think earlier you were saying like some of you are in production with Docker, but obviously not running MySQL in a Docker environment in production. So that'd be interesting to know or to find out maybe more, why that is. I mean, I think we know, but it'd be great to get your feedback. And good to see that some of you are in testing, in testing mode on that. And then the rest of you seem to be either not doing it or planning to or curious. And of course, today's session, is like kind of aims at giving you some, first pointers on what that might mean, running MySQL in the Docker environment. So thanks for your feedback here, and we'll continue with the feedback or with the the information that we would like to share with you on what our experience has been so far, or rather Ashraf's experience, since he's our Docker guru. So I'll hand back over to you, Ashraf. Thanks for now.
Thank you, JJ. So the next component is Docker network. Networking is critical in MySQL. So it is a fundamental resource to manage access to the server from client applications and also from other replication servers. So the behavior of a containerized MySQL service is determined by how the MySQL container is started with Docker run command. A MySQL container can be run in an isolated environment, which is like only reachable by containers in the same network, or an open environment where the MySQL service is totally exposed to the outside world, or the instance simply runs with no network at all. Once Docker engine is installed, Docker will create 3 types of network: host, none, and bridge. So the bridge network, also known as Docker 0, is the default network when you create a container without specifying any networking related parameters. Non-network is simply using null driver, and no interface will be configured inside the container other than localhost. And host network adds container to the host network stack, which means the container will have the exact same network characteristic as the host interface. So bear in mind that hosts and non-networks are not directly configurable in Docker. And Docker also supports a multi-host network out of the box through Docker Swarm overlay network. You can also use other network plugin to extend the Docker network capabilities. We will look into this in the upcoming slides. So host network is pretty straightforward. You have to specify network equal to host in the Docker run command to assign a container to this network. The container will be attached directly to the network stack of the host. So let's say if the host got 2 network interfaces, the container will also have them. And there is no isolation in this network, which means containers created on this network are reachable by containers created inside the default Docker 0 and also the user-defined bridge. Also, the container does not need any forwarding rules in IP tables, since it's already attached to the same network as the host. So port mapping using publish or -p is not supported, and Docker will not manage the firewall rules for of containers that run in this type of network. So this network is only helpful if you want to dedicate the host machine as a MySQL server. However, the packaging is managed by the Docker instead. The default bridge network, also known as Docker 0, will be automatically created by Docker during the installation. Basically, if you don't specify any networking parameters in the Docker run, Docker will create the container under this network. On the machine host, you will see a new virtual Ethernet interface, VETH, as shown in the red box here, and also another one interface, ETH0, inside the container. So Docker utilizes IP tables to manage packet forwarding to the bridge network. So it supports publish parameters where you can run multiple containers with the same image through different ports. And container linking is also supported, where you can expose environment variables and auto-configure host mapping through etc host file inside the between the linked containers. And each outgoing connections will appear to originate from host machine IP address. So the main difference between default bridge network and user-defined network is the embedded DNS service. You can resolve a container's name in the same network to IP address, which is good for simple service discovery among DB containers. Another good thing is this network provides a sticky IP address and host name. So this is the recommended network to run single host MySQL containers, because MySQL relies on proper hostname or IP address for authentication, authorization, and as well as performance. By using IP address when granting a user, MySQL doesn't need to perform reverse DNS lookup when a user is authenticating. So resolving a name could potentially cause problem if the DNS resolver did not respond in a timely manner. So similar to Docker volume plugins, Docker network can be extended to support a wide range of networking technologies. These are the most popular network plugins for Docker, where you can use in a clustered system. So the network can be extended to be running on multi-host networking mode, or support for name resolver and service discovery, and some of them do support encryption. Performance-wise, Calico is the winner because it operates on layer 3. Weave is easy to configure and comes with DNS service. Flannel and Contiv has been long in the market and pretty stable. Each of them has their own pros and cons, and I strongly recommend you to test and compare whichever that suits your workload well. I'm not going to cover them all, since Docker itself already have its own multi-host networking out of the box called Overlay Network, which comes together with Docker Swarm starting in version 1.12. Overlay Network is only only available if you activate the Swarm mode. You can do that by running the Swarm init command, then create a service, and then use the Docker service command to create a service through the Docker service command. So in the default Overlay network, each container will have two interfaces, ETH0 and ETH1. One is connected to Docker Gateway Bridge, as shown in the black box, while another one is connected to VXLAN, VXLAN tunnel through another bridge, represents in green. So the one that connected to Docker Gateway Bridge is the interface that facing the public network. If you try to ping google.com, for example, the container would go through ETH0. If container 1 try to ping container 2 through ETH0, you won't get any reply. And the other interface, ETH1, is solely for container-to-container communication. You will usually get two IP addresses for the overlay network interface. One is the container IP address, or in Swarm term, task IP address. And another one is the service IP address or virtual IP address. So user-defined overlay network is similar with the default overlay, but it comes with embedded DNS server. This is the preferred network when deploying MySQL container as a service. We are going to look into this in more details in the orchestration tools section in the next slides. So the next component is Docker orchestration. So the official Docker comes with 2 orchestration tools to simplify and manage to simplify the Docker containers management at various scales. Docker Compose is another separate package for deployment. With Compose, you use a YAML file to configure your application services. Then with a single command, you create and start all the services from your configuration. Docker Swarm also exposes the same IP, the same APIs as a single Docker host, which means you can use the Docker Compose method against a Swarm through Docker stack command and run your application across multiple hosts. With Docker Compose, you can have all the resources in one text file. On the right side is the Compose file definition with YAML syntax highlighting, equivalent to running the Docker network and Docker run command on the left. You can see the difference where in the Compose format, the definition is structural and more readable than the command line. And it can also work as a template where you can extend this definition with multiple Compose files by using Docker Compose override .yml file. Then another multiple files to then that means you can have one base Compose file and then another multiple files to override some of the options like IP address or environment variables or different environment like development, staging, and production. To deploy what has been defined in the Compose file, we can simply run Docker Compose up command in the same directory where the Docker Compose reside. The -d option is to simply run the container in the background as what we would do with Docker run -d command. You can then stop, start, or destroy everything using the Docker Compose down. Docker Compose also support scale, but you have to ensure that the conflicting options are not there. In this example, we have defined IPv4 address specifically for this container. So scaling our example Compose file won't work in this case. So the scale option commonly being used to deploy stateless applications. Docker Swarm mode is included in version 1.12, derived from another project basically called the same name, Docker Swarm, but it for standalone. So the legacy Docker Swarm use a discovery service like console or etcd to operate. Docker Swarm mode is fundamentally different with huge improvement over the previous version, and it operates using Raft consensus group. There are a bunch of new concepts introduced in this mode, as shown here. Node is basically the swarm host. A manager node dispatches tasks to the worker node, so it can so the container can be deployed on the worker node. By default, manager is also a worker node, so you can disable this behavior and make the manager node as manager only. Another concept is task, which is basically a container in Swarm term. Service is the definition of task to be executed on the worker node. So there are 2 service models, replicated, which distributes tasks based on the number of desired replica, and also global mode, where you run 1 task per available node. Swarm nodes expose service through mesh routing, where all Swarm nodes route to the running container through IP tables net. It also supports round-robin load balancing through IPv4 kernel module. External components can access the exposed service on any of the Swarm nodes. Another one is scheduler, where how Docker Swarm decides which node to use when running container. You can restrict the service to be only located in a certain node by taking resource availability or constraint into the consideration. With Docker Swarm, it's now possible to deploy replicas of our MySQL container for a simple auto failover model. For instance, you can now use Swarm to run a MySQL container with one replica on two Docker hosts and connect to a remote storage system like Amazon EBS or NFS. If the first Docker host goes down, Swarm will schedule a new MySQL container on the other host to keep the number of replica equal to 1. The failover is automatic, but the downtime during failover is almost certain. Keep in mind that this is not a scalable model. The only way to achieve read or write scalability in MySQL is through replication or sharding. So running database containers with orchestration tool requires deep understanding on the how the selected tool schedules, failover, and balance the containers. Covering Docker Swarm will require another session for sure, but here I can give some snippets on what it is capable of doing. Galera cluster with its multi-master redundancy model offers a much simpler way to be implemented inside container orchestration tools. So the database nodes can be treated as equal. All nodes are capable of handling reads, writes, so it's easier for the Swarm load balancer to make decision on this. In this example, if you would like to run a 3-node Percona XRDB cluster, you can use a Percona XRDB cluster image by Percona itself and create a service for a bootstrap only node, and then a service for each of the DB node. So the respective service name will resolve to a virtual IP address, while the respective task.service name, for example, task.pxc1 will resolve to container's IP address. Then use task.pxc1 for db1 and so on to point to the correct database node. Once the cluster is up, you can then remove the bootstrap node service. This to ensure that the WSRAP cluster address will always remain the same for all database nodes when being rescheduled by Docker Swarm. Whenever the underlying containers being rescheduled by Docker Swarm to maintain the one replica, the task name will always remain the same, and regardless of what IP address being allocated to the container. You can then have an external load balancer like Azure Proxy to forward the traffic on services port, which running on 3301, 3302, and 3303 accordingly. Just for a side note, this image that I use here is also supports around a 3-node Galera cluster as a single service, but it requires a service discovery like etcd to monitor and hold the state for each task or container. There are the orchestration tools that support Docker available out there, like Kubernetes, Mesos, and Fleet. Each of them has its own way of orchestration, and the flow are somehow different. You can really you really have to understand on how the orchestration works for each of them before you can fully utilize all the components to achieve high availability and scalability in MySQL. So when deploying MySQL containers using orchestration tool, in general, I'm not referring to Docker Swarm in particular. Keep in mind on these bullets. The first one is try to use placement constraints if possible. So don't let MySQL containers run in the wrong host. Constraints allows you to decide which Swarm node to the container will be placed. Dedicate a number of hosts for DB containers and ensure they are all ending up in those hosts. Another thing is important to understand is the scheduling strategy offered by the orchestration tool. Spread is simply the scheduler schedules tasks on the least loaded node, provided they meet the constraints and resource requirement. Least loaded simply means least number of containers regardless of the state. This is the only supported scheduling strategy for Docker Swarm. Bin pack means the scheduler will pack as many containers as it can on a node. This is supported in Mesos. Random is the scheduler just choose a random node regardless of the available CPU or RAM, and this is supported in the old version of Docker Swarm. Kubernetes got more advanced scheduling option like affinity and anti-affinity, as well as custom scheduler where you can have your own scheduler, which can be written in any language. With Docker Swarm, if you want to update the service, the containers that associated with this service will be recreated, and you can perform this in parallel. For MySQL, this is not a good approach because you will introduce another problem when topology changes happen, depending on the MySQL high availability solution that you are using. To reduce the risk, do not perform this task in parallel. Update only one container at a time and put a delay between them. And then the last topic here, I promise, is cluster control on Docker. We have built an image specifically to make cluster control runs in Docker. We are still improving the Docker support within cluster control, so I would say that it's not for production usage, but I hope that it will be soon. This image comes with cluster control and all of its components and all the dependencies specifically. The image also pre-configured with many stuff required by cluster control like MySQL, Apache, SSL certificates, and also SSH key for cluster control usage. Some key differences with the standard cluster control on host is there are some default changes for cluster control related services to support Docker environment. It also comes with automatic deployment capability, but this only for Galera cluster by using an external script. Cluster control does have a pretty short release, like once every quarter of the year. So you have to upgrade the image regularly to keep up with the latest version. Running with data persistence is the recommended way to ensure continuous upgrade process works fine. We use supervisory to manage daemon inside the container. So if you like to perform service control without restarting the container, you have to use supervisor CTL command line. You can run it in the host network, so you can monitor and manage other database nodes outside of the Docker network, like another physical host or another VM instances in the cloud, or you can run under user-defined bridge network and have your database cluster packed in one single host. And then looking by the name, the image is basically for automatic database cluster deployment. The image there is a one complement image for cluster control. We called it Severalnines /CentOS-SSH. It's a general purpose image that works well with cluster control. And it supports automatic setup of passwordless SSH. With the image, it supports automatic database cluster deployment, where you just need to run a command to create a cluster control, and then another command to create the database cluster. Cluster control will then picks up the database containers after they are started and start the deployment accordingly once it reaches the initial cluster size value. For manual database cluster deployment, it's not really manual. Basically, I would say more to semi-automatic. It's just another extra step for better control on the deployment process. In this method, you create the database containers and then use the IP address or host name of the created containers. You can deploy any kind of supported database cluster through cluster control user interface. And take a look at the example deployment in our GitHub page for more details, where we demonstrate how to deploy a MySQL replication cluster with 1 master, 3 slaves, and 1 proxy SQL. So for add existing database containers, SSH is actually the main communication channel for ClusterControl. So having it run on the monitor host, on any monitor host or container is compulsory. So this step looks pretty hassle though, because most of the MySQL images do not have SSH packages installed. We are going to improve this area in the upcoming version, where this part should be automated or maybe skipped if we find a better method, of course. This is also one of the reasons we came up with a Severalnines /CentOS-SSH image to simplify the deployment process. For more details, go to the link. We provide examples on how to do this with standard MySQL image, which is available in Docker Hub. So what's next? Follow our MySQL on Docker blog post series at severalnines.com, and we are going to have another second series of MySQL on Docker webinar on MySQL container management, which is coming soon. And also try to deploy your database containers using ClusterControl. Before we are going to Q&A session, I'm going to pass the control back to JJ for the last poll question.
Yeah, thanks a lot, Ashraf. Yeah, there's some good resources here, so I do encourage you to check out our blogs if you don't follow them yet. There's a nice blog series on Docker that Ashraf has been writing, and of course we have the second session of our webinar coming in November, so we'll send out some invitation on that soon. But for now, just before we get into questions from your side, if you have any, we want to ask you one last question that's around orchestration tools. And we looked at some of them that Ashraf discussed just earlier, whether it's Kubernetes or Docker Swarm or Mesos. Maybe use other tools or none if you're not really, using Docker extensively yet. It'd just be great to get your feedback here and see, what tools are popular within the audience today. So thanks for providing your feedback. I just let this run for another few seconds, and of course I'll share the results once you've all had a chance to participate. So thanks for that. For now, you can ask questions, of course, in the question section of your control panel. So feel free to ask questions there while we run this poll. But I'm going to close this now and just share the results. Okay, so I guess the most popular tool is to have none for now, but maybe that's not too surprising. I mean, this is all a pretty new topic. But Kubernetes is quite popular. We have a couple of blogs on Kubernetes which are equally popular on our site at least. So if you haven't read them yet, feel free to check them out on severalnines.com. Kubernetes, the blogs there. Docker Swarm and Mesos. Ashraf, you covered a little bit on those two tools in your presentation. So thank you for that. I think we have one question for now, which would be interesting to look at. And it's a question from Francis who's trying to configure a Percona cluster in Docker. And I guess maybe like some feedback on how it might work with replication or not. If you have any thoughts on that, Ashraf, or any recommendations.
So the question is for Percona XtraDB cluster or MySQL replication cluster. I'm assuming this is for Percona XtraDB cluster, and so the replication is actually for Percona XtraDB cluster is basically using the Galera replication. So it's a multi-master replication that use certification-based replication. So you can read and write to any of the nodes, and then the same transaction will be applied to other nodes in sequential order using a GTID. So it doesn't really matter if you have Galera cluster running on Docker Swarm, because the load balancer will just distribute the connection to all of the containers. So it's just if you have Azure proxy in front of it, you can just balance all the services publish port, or otherwise you can just connect to any of the Swarm node which running a service that expose one particular publish port, and then just connect to it and write on read and write from any of the database containers. I hope that answered the question.
Cool. Thanks, Ashraf. And so we're just on the hour now, I guess maybe we can wrap up today's sessions. I don't see any other questions at the moment. So thanks everyone for your participation in this webinar, and thanks Ashraf for the presentation.
Thank you.
That was nice to see. That was nice to see. Like I said at the beginning, we're in Dublin for the Percona Live conference, so we'll probably go back to that. It's wrapping up later this evening. We had some good feedback here on Docker. Ashraf had a talk on Docker similar to this webinar actually, with a lot of interest for it. So it is a topic that people are interested in, especially MySQL on Docker. So just to finish for today, do check out our blog series if you haven't read the blogs yet that Ashraf is writing. They are very popular, and they do give some good insight on what's possible or not with MySQL on Docker at present. And we'll follow up today's webinar with another one, which will be a bit more specific on MySQL container management. And this will be in November, and we will send out invitations on that probably next week. But for now, thanks for joining us today. We'll finish now and wish you a good rest of the day and a good rest of the week. Take care and talk to you soon. Bye-bye.